Okay, whilst we wait for the last few people to arrive, if anyone else is coming. So we have a quiz scheduled, our first in-person in-class quiz scheduled for next Friday. However, as many of you will be aware, the TSSU has announced a strike starting on Thursday of next week. So a few things, I'll talk about the quiz in a moment, but a few things about the strike. I do not know if the TA for this course will be striking, and as an instructor, it's inappropriate for me to ask if he will be striking and what he will be doing. I am proceeding on the assumption that he will be cancelling tutorials and office hours. He may not, but that is not something that I can ask him or should ask him. And as students, you are up to you if you want to ask, but I can't give you that information, which is, so I wanted to explain why I can't tell you that. But you know, all TAs are well within their rights to be striking. Obviously, I have an obligation to you as students, so while I support their strike, I will be continuing to run these classes. I will also be recording the lectures as I always have been and uploading them. So if you choose not to cross the picket line, the lectures will still be recorded and available online as well. So if you choose not to come into class in person, the materials will be available as always. The main issue is the quiz that's scheduled for next Friday. Because of you know, people may not wish to cross the picket line, I think I will reschedule this to Wednesday. I have two options, either to put it online at the same time or reschedule it to another date. I'm highly likely to reschedule it to Wednesday. I'll send out an announcement after I've had confirmation from my department. Okay, so we were supposed to be having a review session next Wednesday, but I will highly likely switch the quiz to Wednesday and have a review session on the Friday. Okay, do you have a question? You look like you have a question. No, okay.
Sorry,
yeah. Wednesday of next week would be the quiz instead of Friday of next week, because this will then fall a day before the TSSU strike starts, and therefore there are no issues with people having to cross picket lines. As the course goes on, this is an indefinite strike, so I do not know by definition how long this will last. If it starts impacting assessments, you know, midterms or quizzes later in the course, then I'll update you as things go. I'll have to adjust on the fly depending on the length of the strike. I will send out an announcement about the quiz though. Highly likely to be next Wednesday though. Any questions about anything I've said? No. Yes.
I think some of you would like to do this online. So maybe
rather than in person. So the issues of doing it online rather than in person is that I can't invigilate it and people might cheat.
Oh.
So that's the reason to have it as an in-person. Can do, but then that also makes it difficult to invigilate. I have to monitor all those people. People might be using messaging on their laptops because it is a quiz on Canvas. So there are issues with trying to do it remotely. So that's why I would prefer to do it in person, at least for this first one as well. Also, if you have questions, it's harder to ask and deal with those on Zoom than it is to deal with them in person. People that will have, there are people that were going to have theirs at their Centre for Accessible Learning. That should still be able to go ahead, but I will update them and they will contact you if that applies to you. Any other questions? Yes.
Well, we have some like practice.
There isn't a practice quiz ahead of this, but what I will say is of the questions that we will have been doing throughout this whole time, they're all very, very similar to what you will experience on the quiz. So things like the practice problems that I've already uploaded, they will be very similar in format to the kinds of things that you would be asked to do on the quiz. So practicing for those, the things that have been at the end of the lectures, whether they've been self-study problems, the worked examples, or questions that I posed to you in class, they'll all be very similar to the style of questions that will be asked in the quiz. There's not a practice quiz, but the questions there are very similar to things you've already been asked, okay? Any other questions? Yes.
So most of the question would be similar to what we did in the lecture.
So what we've done in the lectures and also the practice problems that I've posted on Canvas. Okay, yeah.
Is the material on the quiz going to be right up until Monday then?
I'll tell you the material now. It's going to be on discrete time simple population models. So none of the continuous time stuff will actually appear on there. Okay. Any others? Nope. Okay. That being said, there are aspects, whilst the actual things that you'll be asked to do in terms of analysis, there might be some interpretation things related to that. Things like Allee effects, whilst we've discussed them in continuous time, the same logic applies in discrete time, as would today our discussion of harvesting. So although we're talking about this in continuous time, the same concepts do carry over. So just do bear that in mind. Okay, so today we're going to be talking about harvesting in these simple population models. So we've been talking a lot about, okay, how can we model the growth or decay of populations? And one of the contexts that's really important that we might care about is if we have some natural resource, whether that's, forests that we want to cut down for timber, fishing, if you want to, population of fish in the ocean and you want to fish. We have some resources that are replenishing at certain rates and we want to harvest those resources, but we want to do so in such a way that we're not going to cause the population to crash, and we also want to maximize our yield. So we're talking about how we can understand those things using these population models. So today we're going to go through some different concepts, so constant effort and constant yield harvesting. I'll explain what those mean in a minute. The idea of a yield effort curve, so if you're putting in a certain amount of effort into your harvesting, like what is your yield from that effort and how we can understand that from our models. We want to have generally a maximum sustainable yield. So we want to sustain our populations, but we also want to get the maximum that we can out of them. Okay, so how can we have a maximum sustainable yield? And then some more mathematical ideas here, something called a saddle node bifurcation. So we've met bifurcations before. We're going to meet a new one today called a saddle node bifurcation, and an idea of catastrophic collapse, where a population will collapse from a high level to a low level and go extinct. Okay, so first of all, we want to think about these ecologically acceptable or sustainable strategies for harvesting renewable resources. So like I said, on the one hand, we want to maximize the amount that we're getting out of these populations, but we also want to make sure it's sustainable. So broadly, we can think of two different strategies when we're thinking about harvesting. One is where we have a constant effort. So for example, there's a question down here about when we would have constant effort versus constant yield. A constant effort strategy is, say, where you are, if we take the example of fishing, you have a certain number of boats going out, and the amount of fish that are in the sea is going to determine how much you get out, as well as the number of boats. Okay, so in that case, the constant effort strategy is proportional to population size. So your harvesting rate, which I'll call h of n in this case, is just going to be some constant. So it's going to be proportional to your population size. Constant, a rate times by your population size. The other possibility is if we have a constant yield strategy. So this would be like if you send out your fishing boats, but there is a quota. So you can only catch a certain amount. So in this case, your harvesting rate is just equal to some constant. It's not dependent on the population size. So constant effort, we can think of as being something like fishing without quotas, whereas constant yield would be something like fishing with quotas. And this type of strategy that you'd employ when you're harvesting can really affect the type of outcome that you get. Okay, so let's think about constant effort harvesting. So we're going to suppose that a population of fish, I'm going to focus on fish just because it's an easy thing to think about. We have a population of fish that normally grows logistically, but we're also going to have fishing occurring with a given effort, which we're going to call capital E, which is going to be non-negative. And we're going to talk about the catchability of fish food. by some parameter q. Okay. So how do we write down an equation for these population dynamics? Well, we start off with the NDT. So this is our population size, the change in that population. We're told that we have logistic growth. So let's write down something that looks logistic, Rn times by 1 minus n over k. So there's the logistic growth of our fish population, but we're going to harvest them with constant effort. Now, as I said up here, a constant effort strategy means that our harvesting rate is proportional to the population size. So I'm going to be taking fish away. It's going to be proportional to the population size n. And we're told that we have an effort E and a catchability Q. So all we need to really do here is multiply these parameters together. So we're removing fish with an effort E and a catchability Q. So the more catchable fish are, the bigger this term is. The more effort you're putting in, the more fish you're going to be taking out. Okay. So we can also write this as two separate functions. I call this g of n, and this is my h of n. And I can write this as g of n minus h of n, and again, equal to our net growth rate that we always have, f. So this is just another type of population model. We can do exactly the same things that we've done before in terms of finding our equilibria, looking at their stability and doing that algebraically. But today we're going to be thinking again in a geometric sense to try and understand what's going on with a bit more intuition than you might get out of an algebraic analysis, okay? So I'll leave that as an exercise at the end if you want to go through the algebraic analysis. Okay, so how do we analyze this geometrically then? Well, we looked at phase line diagrams the other day where we plotted this f essentially here, and we plotted our either our net growth rate or our net per capita growth rate, and we analyzed whether we're moving to the left or to the right, and that told us something about the stability of the system. We can also set up a phase line diagram in a slightly different way in thinking about the difference between our positive growth rate, the thing in red, and the harvesting, which is negative in green. Okay. So let's think about what these curves might look like. So let's take a scenario here where, let's just sketch these first of all. So we've got our population size n. And then we're either going to have our growth rate g of n or our harvesting rate h of n on vertical axis. So our growth rate is just the logistic thing in red here, Rn times by 1 minus n over k. That's quadratic in n, and it has roots of 0 in k. So what does that look like? That looks like this. This is 0, and this is k. In fact, before I draw anything else on, I'm just going to copy this to save future effort. One there. Might go a little bit off the page. We'll deal with that in a minute. Make that one a little bit smaller. Okay. So we're going to think about 3 different scenarios here. So that's our growth function, g of n, all of these cases. What else do we have? We have this thing in green, our h of n. So we're going to be subtracting it, but I'm going to draw it rather than doing minus h of n. I'm just going to draw h of n. So that's QE times by n. So that's just going to be a straight line. Q and E are just numbers. So this is going to be a straight line that goes through 0. And I think of a scenario here where it crosses through our parabola like this. So it goes through 0, then it also goes through this point here. This is my harvesting rate h of n. Okay. So let's think about what happens if my population starts off over here in n0. Am I going to be moving to the left or to the right? Remember we did this with our phase line diagrams the other day. We said when the growth rate was positive, the net growth rate was positive, we'll move to the right. And when it was negative, we'd be moving to the left. So here, am I going to be moving to the right or to the left? Where I've drawn this black dot. Right? And why is that? Sir? How do you know the growth rate is positive? You're right, but how do you know that? So the key thing here is that not just that these curves are above zero. Maybe I'll hold that thought. Suppose my n naught is now this other black dot on this right-hand side. Am I going to move left or right?
Left.
Why would I move left?
Because you're harvesting more than you're growing.
Exactly. So although both of these curves are above the axis in this case, this is a bit different to the scenario I said when we draw net growth rate. Our net growth rate is now the difference between these curves. So when the red curve is above the green curve in this scenario, so in this region here, Gn is bigger than Hn, and so we're going to be moving to the right. So you're totally correct that we move to the right, and the reason is because the red curve is above the green curve. But then on this side over here, the green curve is above the red curve, and so our harvesting rate is bigger than our growth rate for the population, and so we're going to be moving to the left. So in this case, we move to the left. And then when these curves intersect, we have a non-trivial equilibrium. It's an n star. If you think about what happens if you were to move this green curve down, so if you were to remove, remember this Hn is just equal to Qen. Suppose we reduce our effort. If you reduce the effort, that E, the slope of this line is going to come down and down and down and down and down. If you got to the point where you put zero harvesting effort in, this term would be zero. Your only intersection would be here along this horizontal axis. This green line, as you reduce the slope of it, would just coincide with this axis here, and you would have an intersection at n is equal to k. And that's just our logistic growth model. So all we've done is we've taken our logistic growth model, we've added this harvesting thing in, and it's shifted this equilibrium to the left. So this n star here is less than k. So what happens if we start increasing our harvesting effort? So we fixed our Q. Now we've got higher harvesting effort. So this is our Hn again. Well, the same logic applies. At our intersection, that's where we're going to get our non-trivial equilibrium, because our harvesting rate is equal to our growth rate. And when the red curve is above the green curve, in this yellow region here, we move to the right. And when the green curve is above the red curve, in this green shaded region here, we move to the left. So again, we've still got a stable non-trivial equilibrium, but the population's been reduced. Okay, let's move over to this side here. What happens if we keep increasing our harvesting effort? Well, eventually, there's going to be some harvesting effort where there's no intercept above zero. So the only places the green and the red things intercept is at zero. So the same logic applies from before, that if the green curve is above the red curve, we move to the left. But that occurs for every value of n. So that means there's no population size. If you harvest enough individuals, the population will crash. So all that's happened with these three scenarios here is because this h of n, this harvesting effort, is a straight line, depends on the catchability and the effort that you're expending. The more effort you expend, this green line is getting steeper and steeper and steeper. The population size that can be maintained, this n star, is moving left. And it eventually gets to the point where there's no population size that can be maintained. Any questions about how I drew that? So how would we summarize this or interpret it? We say that increasing the harvesting effort reduces the equilibrium population until eventually the population is driven extinct. This is fairly intuitive, right? If you keep harvesting a forest loads and loads and loads, eventually there's no trees left, even if they're being replaced at a certain rate. Likewise, if you're fishing, if you overfish, population will be driven extinct. So algebraically, we can think about this as well. We can write this model as dn dt is equal to Rn. That's by 1 minus QE over R minus N over K. So what have I done here? All I've done is I've taken this equation here, and I've noticed that there's a factor of N here. There's also a factor of N here. And I can, if I write the second term as QE over R, then I can put it in the brackets. Okay, so when I multiply out these brackets, I get exactly the same equation they had before. So I've written it in this form because it makes analyzing or finding the non-trivial equilibrium a little bit easier. I'll leave it as an exercise from that form, but it's relatively straightforward. When you set this equal to 0, you can show that the steady state of the equilibrium is equal to K times by 1 minus QE over R. So just like before, when I said if we have a 0 effort, E is equal to 0, then this term in the brackets just goes to 0. It goes to 1, sorry. The harvesting term goes to 0, so the bit in the brackets goes to 1, and we just have our logistic growth with carrying capacity K. But as soon as we have any non-zero harvesting effort, then this gets reduced. And it gets reduced by this factor here. And you can see that when, well, I guess this is the question here. Maybe I should just ask this to you guys rather than telling you. When is this biologically realistic? So for what harvesting efforts is the population viable? That's what this question is essentially asking. So when I say biologically realistic, what do I mean? Not equal to 0 or not a negative number, right? So for this to be biologically realistic, we can only have positive populations, or at least non-negative populations. So what we need is we're essentially asking, when is n star greater than 0? So for this, we need K times by 1 minus QE over R to be greater than 0. So the K is always positive, so that just cancels out. So we can write this as 1. It's got to be greater than QE over R. Or E, our effort has to be less than Q times by R. And I've not got that correct. Our effort has to be less than R over Q. So biologically, this is telling us that, our effort depends on the ratio, or maximum effort that we can have depends on our ratio between our intrinsic growth rate of the population and how catchable they are. So the faster they grow, the more effort we can have. Likewise, the less catchable they are, the more effort we can have. If they're not very catchable, then we have to increase the effort to catch the same amount of fish. So at the start, I talked about the idea of a maximum sustainable yield, that we want to try to be ecologically responsible by harvesting natural resources, but we also want to do it in such a way that we're not expending excess effort that it's costly, that gets us a lower yield, or likewise maybe not exploiting the populations as much as we can. So the way we can think about that is thinking about something called a yield effort curve. So we want to draw a curve where we vary our effort, E, along the horizontal axis. That's something that we're varying. And then we want to work out what our yield is going to be for a given effort. Okay. So we're varying the amount of effort that we're putting into harvesting, and that's going to affect how much we're going to get out. Trivially, we know that if you put in 0 effort for harvesting, you're not going to get any yield. We should also know from, if we go back to these sketches above, if we put in a very high level of effort, you're not going to get anything out either because the population is going to crash. We should be able to know that we're going to intersect at 0 and some other value here. And the maximum sustainable yield will occur somewhere between these two values. If you don't harvest anything, you're not going to get anything. If you harvest too much, the population crashes. There's got to be some intermediate level where you're going to get a maximum amount out of the population, a maximum yield. Okay, so what does this curve look like? Well, our maximum sustainable yield, this idea of sustainable is thinking about what's happening at equilibrium, is going to be looking at our harvesting rate, because that's what we're taking out of the population, at our non-trivial equilibrium n star. This is the amount that we're taking out of the population when it's at equilibrium. Okay, so what we need to do now is substitute n star into our function h. Remember, this h was just our catchability q times by our harvesting effort e times by the population size. And in this case, it's going to be n star. What is our n star? Well, we worked this out on the slide before. It's just this equation here. So if we substitute this in, we're going to have QE n star, where n star is equal to k times by 1 minus QE over r. So all I've done here is I've taken my harvesting function and evaluated it at my non-trivial equilibrium. That tells me how much I'm harvesting when I'm at the equilibrium. So we can see immediately that this is quadratic in E. It's negative in front of the the sign in front of the E squared is going to be negative. And we know we're going to have these two roots here, so we know we're going to reach just one unique maximum value. So how do we work out this maximum sustainable yield? Well, let's think what this curve looks like quickly. I just said it's going to be quadratic. Goes through these two values here. And what we want to find out is we want to find out the maximum sustainable yield. So we want to find out this, I'll call it Y optimal yield that we can have. And that's going to correspond to an optimal effort that we're putting in. So I want to find out what is this point on this graph. So can anyone tell me how I'm going to find out what that point is? Yeah, exactly. So we take our derivative of this y, our yield, so dy dE. So yeah, y is a function of e. What are we going to have here? So we've got a linear term to start with. We've got QE times by k. So this will just be Q times by k. And then if we were to expand out the brackets, we would have a Q squared, a minus E squared over R. So we're going to have minus Q squared The 2 is going to come to the front. We're reducing the power of our e. We also have a k in there, and e, and divide by r. I've got that right, q squared. That's by k to e over r. So what we've done here is we've taken the derivative of this yield curve with respect to our effort. So you said, sorry, I forgot on your name. Remind me your name?
Yeah.
Nien, thank you. Nien, you said that we want to take the derivative of our yield curve. What do we do next? Why did you want to take the derivative? Exactly. So yeah, when is this equal to 0? So if we set this equation here equal to 0, in fact, I'm going to write this as qk times by 1 minus 2q e over r. So you want to set this equal to 0. So y prime of e equal to 0 when, well, the q times by k, they're both positive parameters, so they can't be equal to 0. So the only way this can be equal to 0 is if the thing in the brackets is equal to 0. So this is equal to 0 when 1 is equal to 2q e over r. Which we can rearrange, get our optimal value of e. It's just going to be r over 2q. All I've done here, I've got my yield effort curve. It's telling me how much I'm getting out of the population for a given level of effort when the population is at its equilibrium. I take the derivative of this and set the derivative equal to 0, and that tells me when this curve is changing direction. So that's telling me where this brown dot here is. It's telling me this optimal effort. So this here, this point here is r over 2q. But if we want to find out what the maximum sustainable yield is, we need to find out what this y optimal is. So in that case, what we need to do is we need to substitute y is just a function of e. So we substitute in this y optimal into our original yield effort curve y. So this was equal to q e k, that's by 1 minus q e over r. So now we're just going to substitute this r over 2q into wherever we see e's here. Run out of room here, so I'm just going to move this over. So what are we going to have? We've got an e out the front, so we're going to have the q's will cancel. We will have r times by k over 2. And then in the brackets, we're going to have 1 minus, again, the r's and the q's are going to cancel. So we're going to have 1 minus a half. So we'll have a half in the brackets, so we just end up with rk over 4. This y optimal here, this line going across here, is rk over 4. Does anyone have any questions about how I found the maximum sustainable yield? No? Okay. Okay, so on Wednesday, we talked about Allee effects and how when we have an Allee effect that affects the growth rate of a population, that can mean that we have an Allee threshold, that when the population falls below that, the population crashes. So now we're going to think about what happens if we have harvesting and Allee effects. In particular, if we have a strong Allee effect. So let's set up our logistic growth like we had before, Rn times by 1 minus n over k. We can have an Allee effect. If you remember, we had an Allee effect that looks something like this, n over k minus u over k. Well, here we're going to say is u is positive, and this gives us a strong Allee effect. And we're going to have our harvesting term minus qe n just like we've had so far. So this is our harvesting rate. And here we've got our growth function, g of n, which is now including an Allee effect. So let's sketch some curves. Out a little bit. Do exactly the same process that we've just done a moment ago. Thinking about what happens as we vary the strength of our harvesting effort on this population. So how do we do this? Let's first think about what this growth function looks like. Well, remember when we sketched the phase line diagram the other day? We found it looked something generally like this. The best sketch that will do. So this g of n is cubic in n. And it has roots at 0, at u, and at k. This is our g of n. And once again, I'm just going to copy this. So I'll draw 3 diagrams. Think of 3 different scenarios. Okay, so let's think of our first scenario. So I want to draw on my harvesting rate, and I'm going to assume, first of all, that the harvesting rate is, well, the effort is relatively low. So just like above, we draw on a straight line. I'm going to draw on a straight line that looks like this. This is my harvesting effort. So what does this tell us? Again, we have an equilibrium whenever we have the green and the red curves intersecting. So they intersect at 0, and they intersect twice along this red curve here. So I'm going to call this first intersection N1 star and this second intersection N2 star. And I'll call the trivial one N North star. Okay. So here we've got 3 equilibria given by these gray dots. We think about what's going to happen in terms of the population growing or shrinking. When the green curve is above the red curve, we move left. So between N0 star and N1 star, we move left. When the red curve is above the green curve, we move right. So between N1 star and N2 star, we move right. And again, when the green curve is above the red curve, we move left. So just like when we were doing our phase line diagrams the other day, it's a little bit more complicated now because we've got 2 curves. When our net growth rate is positive, we move to the right. When it's negative, we move to the left. And so we see that N1 star here is going to be unstable because these arrows move away from it. N2 star is stable, and N0 star is also stable. So this is still our strong Allee effect that we saw the other day. Okay, now let's think what happens if we start increasing that harvesting effort and we get to this point here where we're just tangential to that curve. So remember, the reason this h of n changes is that we're just increasing our harvesting effort. And as we do that, the slope of this curve increases. So here we've got 2 equilibria. We keep increasing it to the point that we're just touching that curve. Now we just have 1 equilibrium that's non-trivial. We still have our N0 star down here. Here we've just got 1 value and 1 star. So we've lost one of our equilibria. Carry this on further. What happens if we keep going even further? We've increased the slope of this HN even more. We've increased our harvesting effort further. So the slope keeps increasing. Now there's only this 1 intersection down here at N0 star. So in both of these cases, if we add on the arrows that we had before, when the green curve is above the red curve, we move to the left. So we move to the left here. We move to the left here. The green curve is in fact always above the red curve. So in this case, we always move to the left. This is essentially a knife edge scenario. We've not met one of these cases before where you've got an equilibrium and you always move. You're always moving left here. This is because we're just on a knife edge. This would be called unstable still. And in this right-hand diagram, the green curve is always above the red curve. So again, we always move to the left. It's only on this diagram here where we have a stable equilibrium that's non-trivial. Okay, so why does that matter? What does this all actually mean when we try to translate it back to our population of fish, say? We're harvesting these fish. They have a strong Lee effect in the absence of harvesting. What happens as we increase the harvesting effort? Well, we can see that as we increase this harvesting effort from 0, the population size that's sustainable, this N2 star, is going to start decreasing. And then we're going to hit this point in the middle where there's no sustainable population. So here it's still pretty big, right? You know, the difference between this N2 star here and this, what you'd have in the absence, the carrying capacity in the absence of harvesting, is not that different. It's decreasing a bit, decreasing a bit, and then all of a sudden it disappears. Just like it's been pushed off the edge of a cliff. So we can summarize what this looks like on a bifurcation diagram. Remember we drew these last week, where we have some bifurcation parameter, a parameter in our model that we're varying, and then we want to summarize the stability of that model. Okay, so we draw solid lines here. Solid means stable, and dashed means unstable. And here we're varying this harvesting effort. So we're varying the slope of that line. So let's think about what this looks like. Say, this first slice here is our first diagram, okay? We've got a fairly low harvesting effort. We've got 3 equilibria, just like we have in this diagram on the left. Okay, you keep increasing that until you get our N1 star and our N2 star colliding. This is our second diagram above. We always intersect here, just touch that curve there, so there's 1 equilibrium. And then our third diagram is something like this over here, where we just have 1 equilibrium at the trivial extinction equilibrium. So what it tells us then is that there's a critical harvesting effort where something called a saddle node bifurcation happens. The saddle node bifurcation is where you have a stable and an unstable equilibrium, and they move towards each other, they collide, and then they annihilate each other. So they're kind of like opposites. You can't have a stable and unstable equilibrium together, essentially cancel each other out, they annihilate each other, and you go from having 3 equilibria over here down to just having 1. And this one down here is always stable, so in this region you're always pulled down to 0, you're always pulled to extinction, whereas prior to that you might be existing at this fairly high level. So what does this mean in terms of an interpretation? Did you have a question?
Oh, yeah. So in this case, we're not considering like semi-stable.
Yeah, so technically this is that at EC it's a semi-stable. As a general point throughout this course, whenever we have cases like this that exist on a knife edge, most of the time we talk about them being not biologically realistic, because although it's semi-stable, you're existing on this absolute knife edge that if you get pushed either way, if you get pushed a little bit this way, you have these 2 equilibria, 1 stable, 1 unstable. And if you get pushed the other way, you're in this scenario here. So it's structurally unstable, because a tiny variation in your parameters would push you one side of that knife edge or the other. But good question, yeah, it is referred to as being semi-stable. So how would we interpret this graph? Well, as we increase our harvesting effort, it means that there is a threshold. So above a threshold, a critical threshold, in this case, EC. So above a critical threshold of harvesting effort, what happens? How would you describe this to, or how would you interpret this to someone? Yeah.
It dies.
Yeah, it does. The population crashes. So this is a classic example of kind of, you do some mathematical analysis, you've done, drawn your phase line diagrams, you've drawn your bifurcation diagram, you can interpret this mathematically, what's going on. You've done this for a conservation charity, and they say, what's going to happen? You don't go up to them and say, oh, there's a saddle node bifurcation, because they'll look at you like you're crazy. You have to say, okay, well, what this means is that, your population might appear healthy, and it's fine until it's not, and then it crashes. So having this saddle node bifurcation tells you that the population doesn't just gradually tend towards zero as you start fishing and fishing. Okay, we're fishing, but the population is getting smaller and smaller and smaller and tending towards zero. It's fine. It's not. That's what happens. And this is a really good example of like how mathematical models can be really powerful and tell you something maybe counterintuitive that you wouldn't have thought of previously. I think it's fair to assume naively that you might think, well, okay, if we keep harvesting, the population is just going to gradually get smaller until it's no longer there, rather than that it'll collapse from a high level. Okay, last thing, this idea of a catastrophic collapse. So recall from earlier, we had our maximum sustainable yield, and this yield, our maximum sustainable yield was QE times by our population size at equilibrium. In this model here, it's going to be N2 star. Remember, N2 star is this upper branch here. Okay, so just like before, we can think about our yield effort curve. So this graph here is a yield effort curve for this model where we have an Allee effect. And here again, we've got a stable branch. So this is for our N2 star, and this is an unstable branch for our N1 star. And we saw above that as we increase our effort, these two collide. So if we just plot QE N1 star and QE N2 star, this is what these curves look like. I haven't asked you to plot these because they're a little bit more complicated to plot. But if we want our maximum sustainable yield, remember we drew before a y-optimal, a y-opt, and an e-opt, well, that's our optimal yield, some optimal effort. Right, let me just get rid of this here. Our optimal yield for some optimal effort. What does that look like? Well, it turns out our optimal yield is given by this e-opt down here. Can anyone tell me what they notice about the optimal yield? Exactly. So this is a big problem in conservation and if you're harvesting natural resources, that you might find that your optimal yield to get the most out of this population whilst being sustainable is incredibly close to your critical threshold where the population collapses. So if there's 1 year where there's a few extra individuals die because of there's bad weather, or you underestimate how many individuals, you overestimate how many individuals there are in the population, and you harvest a bit too much. Some fishing boat gets a little bit too eager and harvests a few extra days a year. You can push the population from its maximum sustainable yield down to zero, and the whole thing collapses. So what's going on here mathematically is this saddle node bifurcation occurs very close to the maximum sustainable yield. And this is the concept of a catastrophic collapse. The population goes from this very high level down to nothing. Okay, that's it for today. There's a self-study problem here, which is about essentially doing the algebraic analysis for this model. Any questions before we go? Yes.
Whenever we're considering models like this, Q is always a constant.
In this particular example here, I set Q to be constant. I was thinking of Q as being something intrinsic to, say, the fish, that certain fish populations, salmon might be more catchable than tuna. So that might be something intrinsic or about the population, or even about, how good your fishing nets are or something. So that was treated as being a constant, but it would have the same effect in all of these scenarios here. If you had the same effort, but you improved the fishing nets, or you switched to another species of salmon that was more catchable, say, then it would have Q and E, they multiply together, so they would have exactly the same effect. If you either increase your catchability or you increase your effort, then it would have the same qualitative effect.
I was just wondering if we ever consider like Q as a function of like N of the population.
Oh, as in like, does the catchability itself vary as a
Yeah.
function of N? You totally could, yeah. I mean, in things like if the fish are in a school together, if you have, let's say, your catchability is a function of N. Yeah, if the population is more dense, I mean, these are densities really rather than population sizes. But yes, you could definitely have scenarios where the catchability would depend on N as well. Yeah. Cool. To the person who came in late, I will send an announcement about the quizzes because of the strike next week. It's highly likely that we'll hold the quiz on Wednesday instead. But I will confirm that in an announcement. Okay. All right. Have a good week, everyone, or weekend, I should say, and I'll see you next week.